Okay, let's unpack this. Have you ever noticed how when you overlay two finely patterned screens, maybe like two window screens slightly offset?
Yeah, you see that weird, bigger pattern emerge.
Exactly. That's a moiré effect, a visual trick of interference. But today, we're diving deep into something, well, way more profound. How scientists are using this exact same principle, but down at the scale of individual atoms.
Right. Not window screens, but atomic layers.
To engineer entirely new classes of quantum materials, and these materials have properties that are, frankly, pretty mind-bending.
And what's truly fascinating here is that we're moving beyond just two layers. The focus now is on systems with three stacked atomic crystals.
3 layers.
Which creates what are called double-moiré potentials. And this isn't just, a curiosity. It's a deliberate design principle.
Right, it's engineered.
Exactly. It's leading to tunable, really intricate quasiperiodic structures. And these structures, they're so finely controlled, they can fundamentally alter the symmetry, the spatial distribution of electronic wave functions inside the material.
Wow, so you're actually reshaping the electron's world.
Precisely.
Yeah.
It's not a small tweak. It's really a synthetic platform that lets us explore electronic properties, even whole states of matter that you rarely, if ever, find just lying around in nature.
So our source for this deep dive is a groundbreaking article from Nature Materials. It's hot off the press, and it unveils this incredible phase diagram, basically a map of these double-moiré structures. So our mission today, our goal, is to understand what these exotic new materials actually are.
How they're made, how they're studied.
Exactly. How scientists are managing to create them, probe them, and crucially, why they could be an absolute game changer for the future of quantum technologies.
Sounds like a plan.
All right, let's start with the basics then. Ground ourselves in the foundational concept. What exactly is a moiré pattern when we're talking about atomic layers?
Yeah.
Imagine you have 2 sheets of material, maybe graphene, just a single layer of atoms thick.
Yeah.
Stack them perfectly. Not much happens, right?
Right, just bilayer graphene.
But what if you give one of those sheets just a tiny, tiny twist relative to the other, like barely anything?
That's where the magic happens.
Yeah, you don't just get a simple overlap. Instead, this much larger repeating pattern emerges. That's the moiré superlattice.
It's a macroscopic effect from a microscopic twist.
And its impact on the material's properties is huge. These moiré patterns aren't just pretty, they create these powerful moiré potentials.
Like an energy landscape.
Exactly, like a periodic landscape of hills and valleys that profoundly affects how electrons behave, literally reshaping their energy pathways.
Precisely. These moiré potentials act like a completely new tunable crystal lattice that the electrons actually feel and respond to. And the source gives a great example of this with double-layer graphene, GG.
Right.
If you twist these 2 graphene layers by just about 1 degree, it's famously called the magic angle.
The magic angle, yeah, I've heard of that.
You create something amazing, a nearly flat electronic band. Now, what does flat mean here? It means the electrons in that band move incredibly slowly.
Like hitting traffic on the electronic highway.
Kind of, yeah. Imagine a really wide, flat road where cars just crawl. That's how the electrons behave. And this slow movement, it dramatically enhances how electrons interact with each other.
Okay, so they notice each other more.
Exactly. Which leads to things like non-trivial topology. Think of topology here as a fundamental twist or knot in the quantum fabric of the material. It's robust, hard to undo.
Like the shape of a donut versus a sphere.
Sort of, yeah. A fundamental property. And this unique quantum twist, as the researchers put it, is the secret sauce that leads to these emergent correlated phases.
Correlated phases, meaning the electrons stop acting alone.
Precisely. They start acting collectively, dancing together in complex, coordinated ways. And that's what unlocks completely new, sometimes really weird quantum properties we're only just beginning to figure out.
Okay, so that's 2 layers, mind-bending enough, but you said the real innovation here is adding a 3rd layer. How does that change the game?
Well, it adds a whole new dimension of complexity, literally. The focus of this study is moving beyond just 2 layers to 3 distinct, non-identical atomic crystals, all stacked and twisted.
Non-identical. Okay, so not just 3 graphene layers.
Right. Specifically, this study looks at twisted bilayer graphene, RGGG, carefully placed onto a hexagonal boron nitride substrate, HBN.
Ah, HBN, that's the insulator often used with graphene.
Exactly. So the whole stack is called GGGBN. Now, because you have these 3 interacting layers, you don't just get one moiré pattern. You get 2 simultaneous ones.
2. Okay, how does that work?
Well, first you have the graphene-on-graphene, the GG moiré. from the twist between the two graphene layers themselves. We just talked about that.
Right.
But then you also get a graphene-on-HBN, or GBN-moiré. This forms because one of the graphene layers is interacting with the underlying HBN substrate, and they have slightly different lattice sizes.
Ah, okay, so two overlapping patterns.
Exactly. And the beauty of this double-moiré interaction is that, as the source says, it generates an even richer variety of fascinating structures and electronic properties. It just opens up a massive new landscape for discovery.
More knobs to tune, essentially.
Precisely. But it comes with challenges, big ones. The source highlights how difficult it is to get that precise alignment between graphene and HBN over large areas.
Why is that so hard?
It boils down to a tiny but critical lattice mismatch. Graphene's lattice constant, the spacing between its atoms, is about 0.2461 nanometers. HBN's is slightly larger, 0.2504 nanometers.
Okay, that sounds really small difference.
It is, but
Yeah.
multiply that tiny difference across millions or billions of atoms in a device, and it means getting the perfect twist angle for specific quantum effects is incredibly tricky. Historically, it's been a bit hit or miss during fabrication.
Right, you might get lucky in one spot, but not consistently.
Exactly. And that challenge, that difficulty, actually sets the stage for one of the most remarkable findings in this paper, which we'll get to.
Okay, intriguing. But first, it sounds like an atomic scale jigsaw puzzle with pieces that don't quite fit. How on earth do you even see these tiny structures? You can't use a normal microscope, surely.
No, absolutely not. You're working way below the wavelength of light. This requires some really advanced tools. The primary workhorses here are low-temperature scanning tunneling microscopy, STM, and scanning tunneling spectroscopy, STS.
STM. Okay, how does that work? Is it like taking a picture?
It's more like feeling the surface at an atomic level. Imagine bringing an atomically sharp metal tip incredibly close to the material surface, just angstroms away. So close that electrons can actually tunnel across that tiny vacuum gap.
Quantum tunneling, right.
Exactly. By scanning this tip across the surface and keeping the tunneling current constant, you essentially map out the hills and valleys of the atomic landscape. It's like a quantum version of reading Braille.
Wow, so you can literally see the atoms.
You can map their positions, yes. In this study, STM was crucial for imaging these complex double-moiré structures. And it's even cleverer than just topography. STM can distinguish different atomic stacking arrangements between the graphene and HBN.
Stacking arrangements, like how the layers sit on each other.
Precisely. Things labeled AAB, AAN, AAC. These represent specific ways the carbon atoms in graphene align with the boron and nitrogen atoms in HBN. And each alignment has slightly different energy, which matters.
Okay, and how does that look in the STM image?
Visually, they look for patterns. Bright spots in the images usually correspond to AA stacking within the graphene bilayer itself. Dark spots tend to indicate CB stacking carbon atoms directly over boron atoms in the HBN layer.
Ah, so the brightness tells you about the local alignment.
Exactly. So by mapping these bright and dark spots, they could visualize both the GG and the GBN-moiré patterns simultaneously and see how they interplay.
That's incredibly detailed information.
It is. And they studied a wide range of samples with different twist angles. This gave them GBN-moiré sizes, LGBN, from about 4 to 15 nanometers,
Right.
and GG sizes, LGG, from maybe 2 up to 40 nanometers. A huge range to map out the possibilities.
Right, so they're exploring this whole landscape of possible moiré combinations, which leads to the question, with such a zoo of structures, how do you even start to classify them? Is there like a map for this moiré world?
There is, and that's a key contribution of this paper. How do you organize this richness? They created what they call a moiré phase diagram. Think of it as a map, exactly. The axes of the map are the two moiré lattice constants, LGG and LGBN.
Okay, so a location on the map corresponds to a specific combination of the two moiré sizes.
Precisely. And on this map, they found two main types or phases of materials. First, there are commensurate periodic crystals.
Commensurate, meaning the patterns fit together perfectly somehow.
Essentially, yes. In this context, it means they form truly periodic lattices. Their patterns repeat perfectly and predictably, just like a conventional crystal. On the phase diagram, these tend to form specific lines.
Right.
Geometrically, they're defined by just two independent lattice vectors. They have a rank of 2. And importantly for their physics, they obey Bloch's theorem.
Bloch's theorem, that's fundamental for electrons in regular crystals, right?
Exactly. It means electrons behave as nice, predictable waves with a well-defined crystal momentum. These commensurate crystals also show the usual rotational symmetries you find in crystals. 2-fold, 3-fold, 6-fold. Pretty standard in that sense.
Okay, so that's one type. What's the other?
The second category is incommensurate quasiperiodic crystals. These form the vast background sea on the phase diagram, filling the spaces between those commensurate lines.
Incommensurate, so they don't fit together perfectly.
Right. They lack that simple 2D translational symmetry. Their patterns don't just repeat in a simple grid-like way. Mathematically, their structure needs more than two independent vectors to describe it. They have a rank greater than 2.
Oh, okay, so more complex structurally. Does that mean they're disordered?
No, and that's the crucial point. Despite lacking simple repetition, they possess profound long-range order. It's a different kind of order, not based on simple repetition, but on more complex, non-repeating rules.
An order without perfect repetition, that's hard to picture.
It is. But you can see this order experimentally. When you analyze them using techniques like fast Fourier transform or FFT, they still produce sharp Bragg peaks.
Bragg peaks, those are like the fingerprint of crystalline order, right?
Exactly. Disordered materials give you diffuse blobs in FFT. These quasiperiodic crystals give sharp spots, proving they have long-range order, just not the simple repeating kind. They don't obey Bloch's theorem in the usual way, making their electronic properties potentially very different.
Okay, so you have these perfectly periodic lines and this background sea of ordered but not repeating quasi-periodic crystals. Now, you mentioned something truly surprising earlier about finding perfectly matched patterns.
Ah, yes, this is where it gets really interesting. Let's focus on those commensurate crystals, specifically the case where the two moiré patterns perfectly match up. The 1.1 commensurate case, where LGG equals LGBN, let's call that length LM.
Okay, the perfect match.
Now, if you assume the atomic lattices are rigid, just stiff layers stacked on top, theoretical calculations predict this perfect 1.1 match should only happen at one single point on that phase diagram, specifically at LM equals 12.8 nanometers, the rigid lattice commensuration point.
Just one precise value. So finding it experimentally should be like finding a needle in a haystack.
Exactly. As the source puts it, it should be practically undetectable. You'd need impossibly precise control over the twist angles.
Oh, but
Remarkably, experimentally, these 1.1 commensurate crystals were not found at just one point. They were observed robustly over a wide range of LM values.
a wide range. Like how wide?
They found clear examples at LM equal 10.0 millimeters, 10.6 millimeters, and also the predicted 12.8 millimeters, all showing this perfect 1.1 alignment. This was a big surprise based on the rigid model.
How did they know for sure it was perfectly aligned?
The STM images were incredibly clear. For these 1.1 crystals, they saw a beautiful triangular lattice of bright spots, those AAB stacking sites we talked about. But crucially, there were no visible dark spots.
No dark spots, meaning the GBN pattern wasn't visible separately.
Exactly. Because it was perfectly aligned with the GG pattern, the dark CB stacking sites were essentially hidden underneath the bright AA sites, so the image directly showed the GG lattice structure, unobscured.
Wow, that's direct visual proof.
And the FFT analysis confirmed it. They saw perfectly aligned GG and GBN moiré patterns, resulting in sharp, six-fold symmetric Bragg peaks. Everything pointed to a perfect, robust alignment that shouldn't have been so easy to find.
Which immediately begs the question. If rigid theory says it's nearly impossible, but experiments show it happening readily across a range, what's going on? How can they self-align like that?
That's the million-dollar question they tackled. And their answer is this ingenious self-alignment mechanism. It's driven by a competition, a delicate balance between two energy forces.
Okay, what are the forces?
First, there's the van der Waals energy gain. This is the natural attraction between the layers.
Yeah.
The system wants to settle into the lowest energy configuration, which happens to be when the AA sites in the graphene align with the boron atoms in the HBN that ADB stacking.
Right. Nature prefers the lowest energy state.
But there's a cost. To achieve that perfect AAB alignment everywhere, especially when the lattices don't naturally match, the graphene layers have to stretch or compress slightly. That's the second force, the elastic energy cost.
Ah, so it costs energy to strain the graphene.
Exactly. So the system is constantly weighing, can I gain enough van der Waals energy by aligning to make up for the elastic energy I have to spend straining myself?
A cost-benefit analysis at the atomic scale.
You got it. They built a model, a semi-classical one, assuming the graphene layers are flexible and can relax, while the HBN underneath is pretty much rigid. In their calculations, balancing these two energies revealed something amazing. This 120-degree global self-alignment, the perfect 1.1 state, is actually energetically favored over a surprisingly wide range of LM values, specifically from about 10 nanometers up to 16 nanometers.
That calculated range, Does it match the experiments?
Perfectly. It matches the experimentally observed basin of attraction. That's the region on the phase diagram, shown as a gray area in their figures, around that 1.1 line. If you make a sample whose parameters fall within this basin, even if the initial twist angle isn't perfect, the layers will naturally relax and pull themselves into that 1.1 commensurate state.
Just snap into place.
Essentially, yes. Energetically, it's downhill for them to do so within that range. And the significance of this is huge.
Why is it so important?
Because it means making these complex structures is suddenly much more robust. You don't need that impossible atom-level precision in the initial twist angle anymore. The material helps you out. It self-corrects.
That must make fabricating devices much easier.
Massively easier. It reduces the sensitivity to the unavoidable twist angle disorder that plagues this kind of fabrication. It turns these exotic structures from lab curiosities into something you can actually hope to study systematically and maybe even use.
Okay, that's a fantastic insight. The materials are cooperating, so that explains the commensurate crystals and why they're easier to find than expected. But what about the other main category, those incommensurate quasiperiodic crystals, the background sea?
Right, let's dive into those.
Yeah.
As we said, unlike periodic crystals, they lack that simple 2D translational symmetry. Their patterns don't just repeat.
They're spanned by more than 2 vectors ranked greater than 2.
Exactly. But remember, they still have long-range order, which we see from the sharp Bragg peaks in their FFTs. They're not just random messes.
Ordered, but not repeating. Got it. Now, within this category, you mentioned moiré inner crystals, MICs. What are they?
MICs are a specific type of quasiperiodic crystal. They're quasiperiodic, so no simple repetition. But crucially, they only show rotational symmetries that are allowed in conventional crystals. 2-fold, 3-fold, or 6-fold.
Ah, so they're quasiperiodic in their translation, but conventional in their rotation.
That's a good way to put it. They're sort of an intermediate case, hence the name intercrystal. On the phase diagram, they make up most of the points outside that 1.1 self-alignment basin.
Okay. And does their behavior differ depending on where they are on the map?
It does, interestingly. For MICs to the left of the 1.1 line, where the graphene-moiré, LGG, is smaller than the graphene-HBN-moiré, LGBN, things are relatively well behaved. They show clear GG and GBN periods, sharp Bragg peaks. The quasiperiodic order seems quite robust there.
And to the right of the line, where LGG is bigger.
Things get a bit more fragile. When the GG-moiré cells become larger, the system is more easily perturbed by tiny local variations, like strain. In this regime, the system sometimes prioritizes achieving the locally preferred AAB stacking energy over maintaining perfect long-range quasiperiodic order.
So the local preference can mess up the global pattern.
Sometimes, yes. It can lead to structures that look a bit glassy or disrupted. The long-range order gets somewhat broken up, and you might see the GD Bragg peaks become smeared or less sharp in the FFT. It shows this constant battle between local energy minimization and global structural order.
Fascinating. So even within the quasiperiodic realm, there's nuance. Now for the really wild ones, moiré quasicrystals, MQCs, what sets them apart?
MQCs are the true rule breakers. They are quasiperiodic crystals, but they are distinguished by having Bravais-forbidden rotational symmetry.
Forbidden symmetry, what does that mean?
In standard crystallography, there's a mathematical theorem stating that only 2, 3, 4, or 6-fold rotational symmetries can tile a 2D plane perfectly without gaps or overlaps, while also having translational periodicity.
Okay, those are the only ones that work for normal crystals.
Right. Quasicrystals throw that rulebook out. They can exhibit symmetries like 5-fold, 8-fold, 10-fold, or, relevant here, 12-fold dodecagonal symmetry. Symmetry is absolutely forbidden in regular crystals.
12-fold symmetry. Wow.
And in this specific double-moiré system, because the building blocks have 6-fold symmetry, theory predicts that dodecagonal 12-fold quasicrystals are the kind you might expect to find.
Did they actually find them?
They did. They observed one example experimentally which showed this dodecagonal character, although it was slightly distorted by unavoidable strain in the sample.
Still, finding one is amazing. Are there others predicted?
Theory predicts 2 pristine, unstrained dodecagonal MQCs should exist outside the 1.1 basin.
So why aren't they seen more often?
Well, a couple of reasons. Some theoretically possible MQCs might actually fall inside that powerful 1.1 self-alignment basin. If they do, the system just relaxes into a simpler commensurate crystal instead. It never gets a chance to form the quasicrystal.
The self-alignment overrides the quasicrystal formation.
Exactly. And others might just be extremely delicate, very susceptible to any external disturbance like strain, making them very hard to capture and stabilize experimentally. It highlights how special and sensitive these states are.
Right, it's pushing the limits of fabrication and observation. Okay, so we have this incredible zoo of structures, commensurate crystals, MICs, NQCs. But what does this all mean for the electrons? How do they behave inside these different landscapes? This is where STS comes in, right?
Precisely. Scanning tunneling spectroscopy lets us probe the electronic properties. What energy levels are available for electrons? How do they behave?
So what did STS reveal about the nice, orderly 1.1 moiré crystals?
A key finding was the presence of a flat moiré band in all the 1.1 crystals they studied. Remember the magic angle flat band? Something similar happens here due to the moiré potential.
Flat band means slow electrons, strong interactions.
Exactly. The STS spectra showed a big peak, technically a DIDV peak, which maps the local density of states corresponding to this flat band. And as they tuned the voltage to fill this band with electrons, changing the Fermi level, something crucial happened.
What was that?
The band split into two distinct peaks, separated by an energy gap, about 40 millivolts max. This splitting and gap opening is a classic signature of an emergent correlated state.
The electrons are doing that collective dance again.
You got it. It signals strong electron interactions are dominating, similar to what drives phenomena like Mott insulation or unconventional superconductivity in other twisted layer systems.
And did the electronic state respect the crystal symmetry?
Yes, that was important. The electronic wave function in these 1.1 crystals kept its six-fold symmetry at all the energies they measured. The FFTs of the electron density maps confirm this. It suggests a stable, robust electronic state reflecting the underlying crystal symmetry.
Okay, so the commensurate crystals show clear signs of correlated electron behavior. What about the in-between MICs? What's their electronic life like?
MICs also showed flat bands, interestingly. They found one near charge neutrality that also opened a gap, a bit larger, around 80 milliV, and showed signs of correlation. They even saw evidence of another remote flat band at a different energy.
So similar flat band physics?
Similar, yes, the potential for correlations is there. But here's the big difference. Unlike the stable symmetry of the 1.1 crystals, MICs showed a strong energy dependence of the spatial distribution and symmetry of the electronic wave function.
Whoa, what does that mean? The electron patterns change with energy.
Exactly. As you change the energy, the bias voltage in STS, the actual shape and symmetry of the electron waves change significantly. What might look like one pattern at one energy morphs into something different at another energy.
Why would that happen?
The researchers attributed to the electrons scattering off that complex quasiperiodic potential landscape created by the two incommensurate moiré patterns, GG and GBN. The intricate, non-repeating potential constantly influences how the electrons move and interfere, leading to these energy-dependent patterns.
So the lack of simple repetition in the structure translates to dynamic electronic patterns.
Precisely. It suggests a really rich, tunable electronic behavior that you don't get in the simpler periodic crystals.
Okay, that's super interesting. Now, the grand finale, the MQCs, the quasicrystals. What did STS find there? Surely something exotic.
Absolutely. MQCs also showed evidence of a flat band, this time appearing slightly below charge neutrality. And again, it opened a small gap as it got filled, suggesting correlations are present here too.
So flat bands seem to be a universal feature.
It certainly seems like a robust consequence of these moiré potentials, yes.
Yeah.
But the truly striking observation for the MQCs was how the spatial patterns of the electrons evolved with energy.
Even more dramatic than the MICs.
Yes, arguably. They found the relative intensity of MQC wave vectors is sensitive to energy. In plainer terms, as they swept the energy, the electronic pattern visibly transformed.
Transform how?
It went from looking like incommensurate modulated stripes at one energy to a kind of checkerboard pattern at another energy, and then, remarkably, as they hit the right energy range, it resolved into the actual dodecagonal, 12-fold pattern characteristic of the quasicrystal itself.
Wow, so the electrons actually trace out the forbidden 12-fold symmetry.
At the right energy, yes. It was like the electronic state itself reveals the underlying hidden quasicrystalline order. This dynamic evolution is powerful confirmation of the MQC structure, even in their slightly strained sample. It's a direct electronic fingerprint of that exotic geometry.
That's incredible, seeing the structure reflected so dynamically in the electron behavior. Okay, stepping back then, we've seen these amazing structures commensurate, MICs, MQCs, and their unique electronic properties. What's the big picture takeaway here? Why is this work so significant?
I think there are a few key points. First, these double-moiré structures genuinely represent a unique class of quantum materials. They're not just variations on a theme, they open up new possibilities. And crucially, they provide this powerful synthetic platform for exploring quasiperiodic crystals.
Which are rare in nature, as you said.
Exactly. Being able to design and build them in the lab is huge. It lets us study physics that was previously almost inaccessible.
And the key enabler for actually making these reliably is that self-alignment, right?
Absolutely. The discovery of the self-alignment mechanism is perhaps the most impactful practical outcome. It overcomes a massive fabrication hurdle.
Making the impossible possible, or at least much more feasible.
Precisely. It makes these complex, commensurate, and even quasi-periodic systems robust and accessible for systematic study, reducing that frustrating sensitivity to tiny errors in twist angle. That's a game changer for the field.
Okay, so we can now make and study these exotic materials reliably. What new physics might we uncover? What are the potential applications or future directions?
Well, this is where it gets really exciting looking forward. The expectation is that these platforms will allow us to explore some truly exotic quantum phenomena.
Such as?
Things like unusual forms of magnetism, magnetic behavior driven by the unique geometry, and strong correlations may be different from anything seen before. Also, potentially discrete scale invariance, where physical properties look the same at different zoom levels, like a fractal.
Fractal quantum physics.
Kind of, yeah. And of course, the big one for many, exonic superconductivity. Could these structures host new kinds of superconductivity, perhaps more robust or occurring under different conditions? It's a major driver for the field.
That would be transformative.
Absolutely. But there's a caveat, a challenge. The source explicitly states that these emergent phenomena are often not amenable to analysis by conventional band structure theory.
Meaning our standard textbooks and tools don't fully apply.
Largely, yes. The physics here, especially in the quasi-periodic systems, without simple translational symmetry and with strong electron interactions, pushes beyond the limits of our standard solid-state physics toolkit. We need new theoretical frameworks, new ways of thinking, to fully understand and predict what's going on.
So it's not just discovering new materials, it's pushing fundamental theory too.
Exactly. It's truly frontier science.
So reflecting on all this, what stands out most to you from this deep dive? For me, it's just mind-boggling to imagine engineers literally building materials atom by atom that exhibit properties forbidden by conventional physics, magnetism, superconductivity, all tuned by twisting layers.
Yeah, I agree. This whole exploration of double-moiré potential, seeing how you go from the intricate geometry, the surprising self-alignment, through to these incredibly rich, energy-dependent electronic states. It just showcases the immense power we're gaining to create materials that don't just mimic nature, but can actually surpass the complexity we find naturally.
Designing quantum matter from the ground up.
Exactly. It really pushes us to think differently about how we synthesize and explore matter at these fundamental scales, knowing that entirely new phenomena might be waiting just around the corner with the right twist.
Which leaves us with a tantalizing thought. What other fundamental properties, what new forms of matter could we uncover or even deliberately engineer if we could achieve even more perfect control over these subtle, twisted atomic symmetries? What lies beyond the dodecagonal? That's definitely something to mull over until our next deep dive.